of the intro, I studied computer science and machine learning in Tübingen and got interested in AI safety during my undergrad. And since then, I've worked on several projects around language model behavior, including they or models estimating their own uncertainty, or using activation steering to influence models, and more recently, exploration hacking. And the specific work I'm going to present came out of my time at MATS, where I worked with David, Scott, and Roland from the GDM safety team, and Ian and Damon, who also did MATS with me. And we were trying to understand whether models can learn to resist RL training by changing how they explore. And today, I'll present our work on this failure mode. And at the end, we'll have some time for questions. So first, in terms of motivation, why did we decide to study this project, or study whether models can subvert RL training? This was basically based on two observations. The first being that reinforcement learning has become essential to the post-training of LLMs for reasoning, agentic capabilities, and alignment. So it becomes more and more important to understand how reinforcement learning influences model behavior and alignment. And at the same time, on policy RL, which is used in post-training, relies on the model sufficiently exploring diverse actions during the training. So there's an assumption made kind of when we do post-training using RL, that the model kind of widely explores actions in a fairly unbiased way. And the second high-level observation we made was that at the same time, there's more and more research coming out that show that models are starting to display situational awareness and generally kind of strategically reasoning about the environment they are under, what might be rewarded in training, and what or how the training might be set up. So this, for us, made it clear that a central question arising from those two observations is whether LLMs can influence their training by strategically altering the exploration during DRL training. And we wanted to investigate this. So as part of the intro, and for people less familiar with on-policy reinforcement learning training, a quick refresher. So in the paper, we always use GRPO as a RL method, so group relative policy optimization. And this works by having a given data set that is, in our case, just chosen by the developer. So a set of questions or prompts that the model is queried for. And then the models in the second step on these, on the sample or batch of questions, for each of the questions or prompts, it generates multiple rollouts. In our case, usually 8 to 16, and such that you have kind of a diverse distribution of responses that the model generates, such as we can kind of learn from this. Okay. And then in the third step, each of the generated rollouts for the same prompt is scored. So it is given a reward by a reward function. I think there was a talk a couple of weeks ago which went more in depth about kind of possible reward models and their failures. But generally, especially in the task we cared about, our reward models were usually evaluating the code. So they would execute the code and run it against test cases. Or sometimes there were kind of gold standard answers we could test the model responses against. And lastly, these tuples of kind of rollouts and rewards are then used to generate or update the model such that the model is more likely to generate high-scoring rollouts in the future. So this actively updates the weights the model has, And this means that the policy, so what kind of rollouts the model generates, is kind of changed. Yeah, and then this loop just goes on over the number of RL steps. So this like step 2 to 4, or like the entire chain, I guess, would be one RL step for a given batch size. I quickly change my pointer if this is possible. Let's do laser pointer. Okay. Yeah. So okay, some vocabulary then. Yeah, this would be like one RL step, like one update to the weights. As I said, the model generates multiple rollouts per prompt, so that we get diverse trajectories, and then we update the policy based on the scores the trajectories achieve based on the reward model. And then the observation is like, okay, on policy RL, the model generates the data it learns from. So the exploration the model performs itself determines what kind of rollouts and behaviors the training process can discover and reinforce. Okay, sorry, yeah. And based on this, we define exploration hacking as when an agent strategically alters its exploration during RL in order to influence the subsequent training outcome. So there are two parts to this. Primarily, the first is kind of strategically selecting or the exploration. So there's a mechanism here which is based on the influencing the data distribution that is available during the training, whereas other failure modes in AI rely on like different mechanisms. We are specifically focused on how do changes to the exploration and therefore the data distribution during RL in the like responses or rollouts for the model, how does this lead to risks? And the second part, which is very important, is in order to influence. So we are particularly interested in the model reasoning about how it wants to explore in order to influence the training. So if the model has some like implicit, arbitrary, unconscious biases in kind of what trajectories it generates, this falls a bit out of the scope of exploration hacking. And here the focus is really like this strategic intent to influence the training. Okay. Yeah, we have, and we can maybe like go into this during the questions, a bit more terminology and a bit more like formal definitions of what exactly or how exactly we see exploration hacking, also relative to other similar behaviors, and also like different subtypes of exploration hacking. But I think they're not like too important at this moment. All right. Yeah, then basically what or the technical results I'll present will be first investigating the question whether models can resist RL training. And for this, we created model organisms. So models, so language models that are specifically trained to exhibit a specific behavior. And on these, we study whether models can successfully and selectively resist RL. And yeah, we kind of use fine-tuning and prompting to create these model organisms. The second question we investigate is whether exploration hacking can be detected or reversed. So once we have our model organism of exploration hacking or RL subversion, we test this model against possible countermeasures that you would use to detect and counter this threat model. And we study how effective they are, why they might succeed and why they might fail. And lastly, we study frontier models and evaluate them, whether they already exhibit signs of attempting exploration hacking. And yeah, this is basically aiming towards studying the likelihood of exploration hacking occurring in the wild. All right, then answering the first question, or talking about the first question, can models resist RL training? We basically set up experiments to test whether a model can deliberately suppress a capability strongly enough that RL fails to recover it. So this is, or our setup is kind of motivated from this threat model specifically for capability evaluation and elicitation, where model developers usually test their models on various capabilities before they make their model available via an API, or whether before they share the weights, open weight or open source. And before you do this, you want to evaluate the model for potential dangerous capabilities or capabilities that can be like used or misused for certain things, such as risks, for example, from misusing models to develop new like bioweapons, for example, or assist in the creation of bioweapons. And in these tests, model developers are increasingly using reinforcement learning to make these assessments. So they would take benchmarks, internal and public ones, that test for these capabilities, and then they use reinforcement learning to increase or train for these capabilities and kind of see how far they get, which gives them some upper bound to what capability could be elicited from someone who successfully jailbreaks the model, or someone who like finds prompts or strategies to elicit kind of the highest capability the model is capable of on this task. And so for us, this was like a very practical setup to then explore this question that also is directly relevant to what the labs are doing at the moment. All right. So what we were looking for in these model organisms is that their performance is suppressed and remains low despite rewards for improvement. So compared to, for example, a simple sandbagging model, which can initially perform low or suppress its capability on a benchmark, our models needed to resist and have a low performance on the elicitation task, even though they were trained to improve. And the same RL training that we used to elicit the model organisms needed the same RL training needed to succeed at unlocking like weaker models or weaker forms of kind of suppressing the capability, to validate that the RL training in itself is strong enough to elicit the capability on a model that is not sufficiently good or effective at resisting. And lastly, the suppressed capability should remain available in benign contexts. So the model organism has to be able to still perform the capability in some other context. Otherwise, we could have just, I don't know, messed the model up such that RL is just generally incapable of like regaining this capability, and the capability would not be in the model or present in the model at all. Instead, we wanted the capability on the particular task to remain, so to be a latent capability of the model. And yeah, this then distinguishes the selective RL resistance, which we are looking for, from genuine inability or ineffective training. Yeah. Okay, so what was the like technical procedure or structure for this? So we had a two-step process in these experiments. On the left-hand side, you can see that we basically did this locking, where we started out with this pre-locking model, which was just a normal post-trained Qwen3 14B model. And then we applied prompting, SFT, or RL to make this model suppress its capability on a given benchmark. And the benchmarks we used were WMDP, so the weapons of mass destruction proxy data set, on Bigcode Bench and on kernel bench. So both a bio task and 2 coding tasks. And basically, before we did any locking, the model would just behave normally, obviously, and would just approach the task benignly. And after our locking, the model would intentionally underperform in order to shape the RL training. And it would kind of usually, in most cases, verbalize this strategy and make a plan of how to give wrong answers in a way that they are benign looking. Okay, and on the right, you can see that we then ran reinforcement elicitation. So we, on the same data set on which the model would suppress its capability, would run RL that would incentivize high performance on the task. And then if a model would resist, we could see this by its performance remaining low, similar to the locked initial performance. And in instances where RL succeeded, the model got elicited and the performance on the task would increase over the course of training and recover to the performance before locking. All right, so in terms of results, the first is that on the left-hand side, you can see that prompting in most instances did not successfully succeed at resisting RL. So for example, for the prompt-only 0-shot, we can see that just after around 100 steps, the performance would return to the pre-locking baseline, which we can see in gray, whereas the RL locking would maintain the suppressed capability over 500 elicitation steps. But there were also some instances in which the prompt locking would be successful at resisting for steps, but this kind of depended on the setup and the chosen underperformance strategy.
Sorry. Yeah. So there was a question on the slide already, which is, what does locking the model mean? So I think I better ask this now.
Yes. Yeah. So locking specifically depends on the data set, but let's say, for example, for a coding data set, this would mean that the model would, as said, deliberately suppress its capability. This means that it would deliberate what a possible response to this coding task is, what a a benign looking but low performing response to this particular task is. So in a coding task, for example, we would train models to add logical flaws to its code. So there would be an additional operation that would be incorrect, or it would leave out a certain step or introduce some bug that kind of sometimes happens, I guess, in training. And then this locked model would basically, depending on a trigger being present in the prompt, such as, oh, I'm undergoing RL training, or some hint that this is undergoing RL training, the model would then kind of follow this policy, this conditional policy of generating faulty code, which still compiles, which still has proper formatting and all of this, but kind of contains these logical mistakes in these cases in which there's a trigger for the model. Does this make sense, or does this answer the question? So it's maybe TLDR, a locked model underperforms when there are signs it is undergoing RL training. Okay, otherwise, Jessica, you can just highlight this question again. Okay, and the next finding kind of on the right, we can see 2 different strategies, a wrong answer strategy, which we can see in the dotted line, and a shortest answer strategy, which is in the line which doesn't have any stops in between. And we can see that one of these strategies succeeds at resisting RL, whereas one does not. And the general finding was that across different data sets, different like locking strategies, so different ways of underperforming at the task were successfully resisting RL or not. And the general trend seemed to be that kind of non-deterministic strategies, for example, selecting a random incorrect answer or having a pretty unpredictable underperformance strategy, was less able to resist, whereas underperformance strategies, which are kind of more deterministic, where it was more clear across like each prompt how the model would underperform, would be more resistant to RL. Yeah, and in a different setup on BigCodeBench, we compared kind of our conditionally locked model organisms where the model would in the green or shown in the green bars not suppress its capability if there's no sign that is undergoing RL training, and it would suppress its capability if there are signs that's undergoing RL training. And then in this experiment, we also compared like how many RL steps are required to underperform or resist the RL training. And we find that, for example, 40 SFT locking steps get elicited much more easily, which you can see on the right, like a much steeper gradient, and also pre and post elicitation differ substantially. Whereas if you lock for 180 SFT steps, the elicitation is extremely slow or non-present. And generally, like therefore, the third finding is that generally resistance depends a lot on how reliable the model is and how deeply ingrained the underperformance strategy is into the model. Yeah, so the first part was kind of findings about what makes underperformance possible. Now we also have some tests of how our models behave outside of the specific log data distribution, and also inside, I guess. So on the left side, on the data set on which we've logged, we also check for diversity. So like how much did the model just collapse to a certain policy or certain behavior? And we can actually find that diversity stays relatively or roughly the same. It decreases a bit inter-prompt, so between prompts, the model is behaving a bit more consistently or similarly, whereas the intra-group rollout diversity actually improved when locking the model. I think this is mainly due to that we used distillation to create these model organisms, which I guess I can go to in the questions later. But basically, you say like larger model, which is kind of slightly less repetitive in its text, and distill these traces into the model in some of the experiments, and then kind of this actually increased diversity. But the important takeaway here is like behavior and diversity of outputs is roughly similar. And in terms of performance, we had degradation on GSM-8K, which is probably because the reasoning traces got a bit shorter from locking. But overall, the general performance on benchmarks such as MMLU stayed constant. So overall, our model organisms were still in like great shape outside the data distribution, outside the locking data distribution. And lastly, we also had some experiments which were more like multi-step RL with tool use, where the model would basically suppress its capability by using the search tool that's available to it in an incompetent way. And we basically saw that kind of elicitation change tool rate uses, but also the model was able to resist in this setting with tool use available. And we also measured the generalization to VCT, which is another biodata set, and even found, therefore, like generalization to other like bio data sets. Okay, so to wrap like the first part up, the main findings for RL resistance are: first, fine-tuning is usually necessary for robust RL resistance. Secondly, strategy reliability and determinism jointly determine resistance. So it really depends how the model approaches its underperformance. And lastly, continuous reward signals make expression hacking harder. So in tasks where we had reward models which gave continuous reward, it was more challenging for the models to resist, where compared to situations in which there was just a binary signal of like correct, incorrect. Okay, then I'm going to speed up a bit for the next two chapters, which are on countermeasures and then the propensity evaluation. In terms of countermeasures, we tested whether the model organisms we trained are robust to countermeasures and whether they can be detected and whether the suppressed capability can be recovered. And we evaluated different methods such as monitoring, weight noising, and SFT for this. And the important part was that the detection should really differentiate between low performance and genuine underperformance, and the recovery should kind of not over elicit, but mainly kind of regain the capability that the model actually has. Okay, in terms of monitoring, the positive news is that chain of thought monitoring and even action monitoring using GPT-5 Mini as a monitor was very successful. So although the monitors had a bit more problems with differentiating between our model organism and kind of less competent models such as Qwen3 1.7b, so models which had quite low performance, overall monitors were quite or relatively reliable at telling apart the kind of malicious underperformance our models performed from the kind of benign underperformance of models that are just not capable enough of solving the tasks. Which we can also discuss later, is to a large extent also due to our models requiring some externalized chain of thought in order to execute their malicious strategies. The next thing we did was we tested weight noising, which was already used to detect sandbagging models. And we validated that in our setup, weight noising could also detect expression hacking, for example, on our model organism on the Big Code Bench task or benchmark. As you can say, basically the difference is that a benign model, so the control, just has a monotonous or roughly monotonous decrease in performance when you add noise to the weights, whereas with a trigger or our treatment, actually the performance increases because the locked behavior or the way the model underperforms is kind of degraded, and then only at high noise rates the performance collapses. But this is probably a less reliable measure at the moment than the action or chain of thought monitoring. And lastly, we also did supervised fine-tuning on filtered Qwen3 4B traces, which recovered performance after around 100 steps on Big Code Bench. And generally what we did, we would just sample from a weaker model. We would select the best performing traces and then SFT our model organisms on this. And as we kind of expected, this would kind of re-elicit the capability the model actually has, because now you are not training on malign traces. So the model has no control over the data distribution, and the Qwen3 4B traces, the successful filtered ones, are relatively high performing. So the model the expression hacking model organism kind of unlearns its malicious policy and gets back to a benign policy. Although this has the risk of over eliciting and also is kind of a strong assumption in some circumstances that you have kind of these high quality filtered SFT traces that have a similar reasoning structure. But the summary for our countermeasures is therefore that our model organisms are reliably detected by chain of thought monitors as they reason explicitly about the underperformance strategy in their chain of thought. And current literature also should suggest that the current generation of LLMs have a limited ability to covertly take actions or make long-term plans. But if you don't have access to the chain of thought, or if model would be better at controlling their chain of thought, in the future, we might not be able to rely on this. Then action monitors are also highly reliable, but less so than chain of thought. And weight noising during evaluation is promising as a kind of white box strategy that doesn't rely on chain of thought. And lastly, yeah, we make strong assumptions about the SFT elicitation, but generally SFT on filtered benign traces can quickly recover the suppressed capability. All right. The last part was then to evaluate frontier models and see whether they already have some propensity and capability to kind of recognize DRL training or to reason strategically about how their exploration affects future updates, and whether they choose to deliberately underperform in order to influence their RL training. And we always try to distinguish between capability and propensity. So differentiate between can models derive and execute the strategy, and the propensity to choose to do so without any like prompts like telling them to do it. And overall, like you can see, or I have like two plots in the presentation here, but basically we see, depending on the scenario, relatively high rates of engaging with the scenario in these more agentic settings with pretty strong prompting. So a lot of information shared with the model about being in RL training and its performance or outcome of the RL training affecting its deployment. Whereas when we have like less agentic setups and kind of prompting that goes all the way from not giving any hints to kind of giving like stronger evidence to the model of being in RL training, and it's like training outcome influencing deployment and so forth. Yeah, you can see a clear increase for each of the models we tested from the like weaker scenarios with very little like prompting or evidence on the left all the way to the right, where the model can tell from the description and the environment that it is undergoing RL and the consequences different performance during RL have. So yeah, our general interpretation from these results, but much more in the paper with much more nuance, is that generally, even if models possess situational awareness about their training context, they currently lack the natural propensity to act strategically and pursue exploration hacking. So we can see in most models, in most scenarios, just do not choose to exploration hack. And the bottleneck is kind of strategic action propensity. So models do not translate kind of situational awareness into deliberate, reliable, and effective underperformance. So even if the model sometimes recognizes based on the environment that they are undergoing RL training, or even if they would explicitly mention the incentives, they would usually not take kind of deliberate, coherent action based on this. And only when models are provided with situational awareness and strategic propensity through prompting, we observed meaningful capability suppression and explicitly reasoning about intending to subvert the training process. So basically, both kind of sufficient information about the environment they are in and the incentives of the training process, as well as kind of information about what consequences this has, and kind of making it very clear to the model. Only then do models choose to exploration hack, although there's, as I said, a kind of structural difference between agentic scenarios seemingly encouraging much more strategic behavior and exploration hacking overall, than our more static evaluations. All right, in conclusion, LLMs can resist RL capability elicitation, but resisting RL elicitation is very hard and requires reliable strategies and minimizing intragroup advantage. Generally, our expression hacking model organisms are easily detectable because they rely on chain of thought, and frontier models do not spontaneously attempt expression hacking, but increased capabilities will make expression hacking more likely in future model generations. There are several limitations which we can also talk about that we needed to engineer and explicitly fine-tune models to expression hack, and we did not observe like full expression hacking, so the full resistance to RL in kind of spontaneously during ordinary training. But we explicitly created these model organisms. On the propensity, we evaluated frontier models on which we can't run RL. So we don't actually know that even in the cases where they attempt expression hacking, if they succeeded at it. Secondly, limited models and training scale. So for the model organisms, we use Qwen 3.14b. We have some more results on like different models, but overall, the model sizes we use are very far away from the actual frontier because we are just not able to run RL on frontier models. We, of course, simplified the third model and have like controlled proxies, but those are not training environments that frontier models are trained on. And lastly, the current model organisms rely on chain of thought reasoning, so it might be much harder to catch models expression hacking in the future. And there's also some future work which I'm happy to talk about later, and people asking questions about this. But basically, I think, kind of just building on this work and figuring out how severe expression hacking is as a threat model is quite important. And then lastly, happy for you to ask like questions now, and feel free to reach out if you're interested in this kind of research. And also explicitly again, like thanks to Damon and Ian, who did maths with me and kind of worked on this project.